Chapter 2 is about algorithms analysis. Algorithms analysis. Introduction. Computer programming. Learn by experience. We learn by seeing solved problems and solving new problems by ourselves. How do we learn? We learn by seeing solved problems and by solving new problems by ourselves. Studying various problem-solving techniques and by understanding how different algorithms are designed help us to solve the next problem that is given to us by considering a number of different algorithms. We can begin to develop pattern so that the next time a similar problem arises, we are better able to solve it. When an interviewer asks to develop a program and an interviewer, what are the steps that the interviewee should follow? We will be taking a systematic approach to handle the problem and finally reaching to the solution. Algorithm. An algorithm is a set of steps to accomplish a task. An algorithm is a computer program. Is a set of steps applied over a set of input to produce a set of output. Knowledge of algorithm helps us to get our desired results faster by applying the right algorithm. The most important properties of an algorithm are correctness. The algorithm should be correct. It should be able to process all the given inputs and provide correct output. Efficiency. The algorithm should be efficient in solving problems. Algorithmic complexity is defined as how fast a particular algorithm performs. Complexity is represented by a function of t, the function of n, times versus the input size n. Correctness, efficiency, complexity. Speed. Efficiency is related to speed. Efficiency is related to complexity. The simpler is the faster. Correctness, it always should be correct. Always should be integrated. Always should be accurate. It should be able to process all the given input to provide the correct output. Asymptotic analysis. Asymptotic analysis. Asymptotic analysis is used to compare the efficiency of algorithm independently of any particular data set or programming language. We are generally interested in the order of growth of some algorithm and not interested in the exact time required for running the algorithm. This time is also called asymptotic running time. Asymptotic running time. Big O notation. Big O notation. Definition. Function of n is a big O of Gn, or function of n equals O of Gn, which is function of Gn. If there are two positive constants C and n such that and n0 such that function of n is less than or equals to C Gn. right? Constant c. And this is a function of g, and this is a function of n, and there is a constant. For all n positive, all n greater than n, 0. In other words, c, this constant times gn is an upper bound for fn for all n equals or greater than n0. The function fn growth is lower than cgn. So this is the cgn and this is the function. The growth rate is lower. An example is n squared plus n is a O of n squared. This is an example. Omega notation. This is definition. Function of n is omega of g n, or function of n is omega of gn if there are two positive constants and n0 such that two positive constants c and n0 such that c times gn is less than or equal to function n for all n greater than or equals to n0. And here we see it's the opposite. It's the opposite of the previous case. It's not the outer, it's the omega. Over there it's the O, here is the omega. Omega is down there. In other words, C, the constant times Gn, like this one here, is lower bound for function of n. Function of n growth is faster than this. It's growth faster. Find the relationship of function of n to the power of c and gn n to the c to the power of n omega. Theta notation. Definition. Function of n is theta of g of n. F of n is theta of g of n. Or of n is theta of g of n if there is three positive constants, c1, c2, and n0, such that c1 multiplied by gn is less than or equal to fn, and is less than, which by itself is less than or equal to c2 times gn. So c1 and c2 represent tight bounds or upper and lower bounds for the function fn for all n greater than or equals to n0. Gn is asymptotically tight bound, so this is the c1 gn and this is the c2 gn, and in the middle we have the fn. So now we had the O on the top. If we go up, big O notation on the top, omega on the bottom, lower bound and upper bound, and we have the two tight bound, which is upper and lower, c1 and c2, and the fn in the middle, and we call this theta. All right. Complexity analysis of algorithms. Worst case complexity, average case complexity, best case complexity. Worst case complexity, it is the complexity of solving problem for the worst input of size n. Like the worst input, the most difficult input, and we do the analysis, worst case. It provides the upper bound for the algorithm, this is the most common analysis done. It's very common, worst case. We consider the worst case scenario, okay? Average case complexity is the complexity of solving problem on average. We calculate time for all possible inputs and then take average of it. Best case complexity is the complexity of solving problem for the best input of size n, the easiest one, all right? So when testing, we do the worst case more frequently. For the developer to start testing, they usually do the best case, so because it's more logical and easy to confirm, to validate. Time complexity order, a list of commonly occurring algorithm time complexity in increasing order. Name, notation, constant, O1, logarithmic, O log n, linear, On. N log n, function of n, quadratic, which means square, second degree, right? Polynomial, C is a constant, and C is greater than 1, polynomial. Exponential, and here factorial, or n power n factorial, or n to the power of n. All right. Now each one is explained in the following lines. Constant time, there's an algorithmic say to run a constant regardless of one input size. And here are 5 examples. Accessing the nth element of an array, push and pop of a stack. All these are constant. In Q and remove of Q or DQ. Accessing an element from a hash table, bucket sort. We'll be talking about hash tables later in this book. All right. Linear time, ON, an algorithm said to run in linear time if the execution of the time of the algorithm is directly proportional to the input size. Direct proportional, linear. There's a direct proportion. All right. Example, array operation like search element and find minimum and maximum. They are related to the input size, the array size or the vector size. Linked list operation like traversal, find minimum, find maximum is related to the input size. When we need to traverse all nodes for a data structure for some task, then complexity is no less than On. All right, linear time, On. O a function of n. Now logarithmic time. An algorithm is said to run in algorithmic time if the execution time of the algorithm is proportional to logarithm of the input size, the log of the input size. Each step, so it's not linear, it's logarithmic, it's like a curve, okay? Each step of an algorithm, a significant proportion of the input is pruned out without reversing it. For example, binary search. We will read about these algorithms in this book. Binary search is subdividing the search into 2 halves, and we only search half of it. And we saw a function in the previous video that shows that. N log n. An algorithm says to run in logarithmic time if the execution of the time of an algorithm is proportional to the product of an input size and logarithm of the input. All right. Example is mega sort, quick sort, heap sort. We'll be talking about this later on. Quick sort is a special kind of algorithm to sort a list of numbers. Its worst case complexity is n square, and the average case of simplicity is n log n. So we have the worst case and we have the average case, right? That's how we apply what we just learned. Quadratic time, the n square, quadratic time. Algorithm is said to run a logarithmic time. The execution time of an algorithm is proportional to the square. This is not logarithmic, it's quadratic. There is an error here in a typing mistake, okay? Square of an input value. An algorithm is said to run in quadratic time if the execution time of an algorithm is proportional to the square of the input size. And the examples are bubble sort, selection sort, insertion sort equals to the what? The square of the input size. Deriving the runtime function for an algorithm. Constant loops, nested loops. Deriving the runtime function of an algorithm. Each statement takes a constant time to run, time complexity, constant time. Loops. By running time of a loop is the product of running time of a statement inside the loop, all right? And the number of iterations in the loop, time complexity, is linear, a function of n. Nested loops, a loop inside a loop, all right? The running time of a nested loop is the product of the running time of the statement inside loop multiplied by the product of the size of all loops. So the time complexity is n to the power of c, where c is the number of loops. For 2 loops, it's n to the power of 2. All right? So this is quadratic. Consecutive statements. Just add the running time of all consecutive statements. We're trying to find the running time of a program, okay? If else statement, consider the running of the larger of f block or else block. We consider the worst case, the largest one. Either whatever is the largest, we consider that. And ignore the other one. Consider the worst case. Logarithmic statement. If each iteration the input size is decreased by the constant factor, time complexity equals to log n. Of each iteration if each iteration the input size is decreased by a constant, it's logarithmic. Time complexity examples. The example 1, constant. We have a method called fun1, like function 1, and we identify an integer, then with the loop from 0 less than n, the n is the passed argument, and we say m equals m plus 1 and return the result. All right. So this is constant. Time complexity examples. Okay, this is a proportion to the n, linear. And here we have 2 loops, one inside the other. It's a function of n. Because we have I and j. And we compare I with n and j with n. After this lower loop ends, it will repeat it on the outer loop, then return the sum. Time complexity n square, similar to the previous one. And we pass the n, and we have I and j, and here we compare the I and the j, not with the n. So it's really n square. This is the only difference from the previous one. It's not exactly similar. In the previous one, we are comparing with the past integer, comparing both with the past integer. And the second, we are comparing the j with the I. So every time we are comparing the j with the I, not with the n. Okay. Time complexity that n square using the while statement, where we double I equals double I. All right. Each time problem space is divided into halves, the complexity is log. The next example is the log n. It's divided by half. The counter problem space is divided into half. Then it's way faster. It's the log. Okay. Same as above, each time problem space is divided to a half. Time complexity is log n. So now we have the past argument, then we have I and j and k, and we have a loop for I comparing with n, and then we have the loop for j comparing with n, then we have a third loop for k also comparing to n. All right. So we have, this is called log n, 3 loops. The outer loop will run for n number of iterations. In each iteration of the outer loop, the inner loop will run for n iterations in their own. Finally, complexity will be n times n times n. And this is n cube, like this one here. Okay. Example 7. We have the fun7 or function 7, another method, and we also passing the n variable, and we have the ijk counters, and now the starting point for I is n, not 0. And from 0 to n for the counter I, from 0 to n for the counter j, and from 0 to I for counter I again, and 0 to n for k, and we have 2 summations calculated twice. And we, after final result of this, we continue to add this. These 2 groups of 4 loops, this first group and this is the second group, are consecutive, so their complexity will add up to form a final complexity of the program. So the first one is n squared, the second one is n squared. The time complexity is O(n) squared. Another example where the time complexity is 3/2. because it's n times the square root of n. How can we see that? In function 8, fn8, the same argument will get passed, and we have two counters I and j, and we have the summation, the m, and from I 0 to n, j from 0 to the square root of n, and we find the summation. So the time complexity is n times the square root of n, and this is equals 3/2, because this is a half. 3/2 is 1.5, right? This is 1. The power is 1. Anything, it means the power of it is 1. And here is any square root is half, so 1.5. Just a math, okay? Then we have a method called function 9, at the same passing argument, and the time complexity is log n. How do we see that? The two counters I and j from 0 to I over 2. So it's not increasing by 1, it's getting half every iteration. All right. And this is a regular one. So this is called log n. Each time problem space is divided into half, goes half. So this is called log. All right. Another example where arithmetic aggregation, the time complexity is n square, just like that. I and j counters, I from 0 to n, j from I to 0. From I to 0 goes down. All right. Then we have j minus minus. So this is function of n, n minus 1, n minus 2, and so on. And the time complexity is n squared. Another example where the time complexity is n cube. We have I and j and k, and from 0 to n, from just like the similar previous example, from j equals I to n, and k equals j plus 1 to k to n. So they are depending on each other. This is called n cube. And if we noticed, it's all incrementing. So it's not really similar to the previous one, but yeah. So this is n cube, all right. Another example where it's a linear function of n, I and j from 0 to n, and here j is 0 from 0 to n as well, and they just increase. J value is not reset at each iteration, so it stays. It doesn't really reset. Starts initially from 0, then just continues in the next iteration. Next iteration of I does not reset. This means it's a linear thing. This is really interesting. See here before the semicolon, we have in each for statement, we have the first expression or expressions. It can be several expressions that are comma separated, right? Well, this happens only the first time. In the for statement, this condition is checked before each iteration. This statement or group statements, they get executed after each iteration, right? So here we don't really have anything set before the first semicolon. So the J value is not reset at each iteration. This time complexity is O to the N. Another method, which is also linear, it shows here I and j, but this starts from 1, I to n, and it doubles every time. And here from 0 to I, right? The inner loop will run for 1, 2, 4, 8 because it doubles, n times the successive iteration of the outer loop. Time complexity is 1, 2, 4 on all these, plus n. All right, so it's a function of a linear function. Example 14, calling the function f1 and f13 above and try to find the number of instructions. All right. So output 110,000. So we called function 1, 2, 3, 4. So function 1 to 13. All the functions from 1 to 13 in the previous. And that's how it shows. The analysis, the total number of instructions in the previous functions clearly given us the idea that the big O notation is not perfect and does not give us the exact number of instructions. It also shows that it gives us a good picture of the approximate overall complexity. Overall complexity. So if n equals to 100, the number of instructions, 110,000, 4,957, is that a million? Yeah, it's a million. 20,000, 1,000, 197, 4,950, similar to that. So the execution for the third one is similar to the execution of the, I think, 10th one. And here we have 166,650 and 100 and 134. And master theorem. Let's isolate this in a separate recording.